A very warm welcome to all my dear students. So today was the paper of physics, basically science, and we are going to talk about the part of physics, the solution of the questions asked in the question paper. So in the question number 6, the first A part, we have the first part. Name and state the rule to determine the direction of force experienced by the current carrying a straight conductor placed in a uniform magnetic field which is perpendicular to it. So basically in this question, current carrying conductor is given to you. The straight conductor is there which is having some current. Let us have a conductor and this is holding some current. The current is flowing. Basically the charges, the positive charges are moving this way. Ultimately we have the current in a conducting wire, and a perpendicular magnetic field is there which is also present. Suppose this is the magnetic field we have, which is inside. The magnetic field is going inside. It is going inside the plane. Okay, fine. So we have to determine the force experienced by this. So what I told you, the trick, that motor we use for Fleming's left hand rule. Fleming's left hand rule. So we are going to use left hand rule because the current is a given quantity, and we needed to find out the direction of motion of the charges, motion of the conductor. It means force experienced by the conductor. So we use the Fleming's left hand rule. So magnetic field is going inside, current is in this direction. This is the magnetic field going, this is the current, and this is the upward force experienced by the conductor. So the direction of force is this way, and the rule is Fleming's left hand rule. Okay, now the next part. An alpha particle while passing through a magnetic field gets projected towards north. So in such cases, for the convenience, you should draw north, south, east, west. Now the alpha particles are there. Alpha particles are positive particles, you very well know, as we covered in the theory lectures. So alpha particle is moving towards the north direction. The alpha particles are actually moving this way as per the question, and it gets tilted towards the north. It is projected towards the north. Why? Because of the presence of magnetic field. As I repeat the question, an alpha particle while passing through a magnetic field gets projected towards north. So in such a situation, if I fix the direction of motion of the particle, which means the direction of current, and the direction of force we experience in this situation is this way. So what is the direction of magnetic field? We will get the magnetic field inside the plane going, right? So then only it is possible to get this, because current is a given quantity. So we are going to use the Fleming's left hand rule again. So this is the magnetic field going inside, the current in this direction, and the force experience is in this direction. So we have got the magnetic field. Now let us see the other part of the question. In which direction will an electron project when it passes through the same magnetic field? Okay, so if the electrons are projected, then in the same magnetic field which is we have seen in this situation, which is going inside. If I draw it this way, magnetic field is going inside the plane. So magnetic field is going inside the plane, and the direction of current is not in the direction this way, because it is now a electron which is opposite to the direction of motion. So if the direction of motion of electron is this way, so current will be in this direction. So we have magnetic field and current. Now we are going to use the Fleming's left hand rule to detect the direction of thumb for seeing whether the electron will move upward or downward from the Fleming's left hand rule. This is the magnetic field going inside, and this is the direction of current which is at this side towards the west. So this is what done. Now, as we can see, the thumb is going downward. So it means that the charges will experience the force in downward direction, and the charges will experience, as they will experience the force downward direction, so they will tilt themselves towards the south direction. So the answer is they will be tilted, they will be projected towards the south. As the alpha particles were projected towards north, they are projected towards the south. Now the next question, what is a solenoid? So if we talk about the part of solenoid, so basically it is asking about the solenoid. When the current passes through any conductor, it shows the magnetic field around it. Basically a moving charge shows magnetic field around it, a constant magnetic field, a uniform magnetic field around it. This we have covered in the video lectures. Now, a coiled with n number of turns on any material, a cylindrical material. Let us draw. Suppose this is any rectangular material, and on this material we are going to draw the circular loop of the coil. This is the loops, the circular loops. And if we connect this through a key with a battery, then what we found, the current is flowing in the circular loop of the solenoid. Always remember, from the positive terminal the current comes out, and the current goes in to the negative terminal. Okay, so we are very well known about the direction of current in the loop. It is given this way. So my thumb is detecting the direction of magnetic field. So we will have a magnetic field from center part. If I talk about, we will have a straight line magnetic field, because it is the result of all the magnetic fields vector additions. So this is the magnetic field we are getting. If I draw the other lines as well, this is the line. This is the line of magnetic field we are getting. Okay, always remember one thing, as I already told you, which will come in the next asked question, that is, why does the magnetic field does not intersect with each other, the two magnetic field lines? The reason I told you, because at the point of intersection there will be a two tangents, and which detects the two direction at the same point, which is not possible. An individual direction at a point is there of either electric field, magnetic field, or a gravitational field. Okay, so solenoid is done. The pattern of magnetic field lines of the magnetic field produced by a solenoid through which a steady current flows. Okay, so this is what we are done. We have explained and we have drawn both. Okay, now let's move to the next question part. The next question is, three resistors R1, R2, R3 are connected in parallel, and the combination is connected to a battery, ammeter, voltmeter, and a key. Draw a suitable diagram to show the arrangement of these circuit components along with the direction of current flowing. Okay, so we have a battery first, the source who provides the flow of current. Then the key is connected. Then we have three resistors connected in parallel. Suppose this is the third resistor. Then second. Then first resistor. This is R1, R2, R3. They are in the parallel combination. Parallel combination simply means that the current will be divided. Okay, so now we are going to connect the voltmeter and ammeter in this diagram. So if I talk about voltmeter we always connect parallel to the resistors to detect point to point change in the potential difference. Okay, so if I give the name A to this terminal, so until the resistor comes, the point will be same, because we are taking these connecting wires of negligible resistance. So this will be point A, and this all are point A. If I say this point is B, so this will be B, this will be B, and this will be this. These all point will be B. So we basically connect the voltmeter across A, B potential difference. Okay, so we get the potential difference across as V volt. The geometry can be of any type you can have. Okay, now if I talk about the emitter to be connected, so there are the three different currents, as we know, that quantization of the charges and the quantization of the charges of flows with respect to time. That is what current we talk about. So total current is I. Here I have total current I. Now some part of the current goes as I3, then some, and then here we have the remaining part, I minus I3. Now here I2 current goes, and here I3 current goes, and all the combination is actually I2, I1. This is I1, and then this is I3, all together combined to give again I. So whatever the current is drawn from the battery one terminal, it will be received by the other terminal as well, because of the conservation of the charges flow. And this is what the circuit diagram we have. Okay, so if I talk about the emitter to be connected, so emitter will be connected in series of individual resistor to measure how much current is being drawn from the battery to be consumed by the particular resistor. So this is A1 resistor, A1 emitter. This is A2 emitter. This will be A3 emitter. You can connect this side or this side of the R1 resistor length. Okay, so we are done with this part. Now if we talk about the next part, in this part we have this as a parallel combination. So in this parallel combination, what we are going to do is, this is series, let it be from the point A to point B we needed to find. If I talk about the mid part, equal resistors are there, then R equivalent 1 is equal to R upon N, because equal resistors are given. You can do it from your traditional method as well, 1 upon R2 plus 1 upon R3, you will get the result same only. So this is a 10 upon 2, because N number of resistors are 1, 2, and the resistor is 10. So you are getting 5 ohm as the value between C to D. This is point C, this is point D. You are getting the conclusion of a 5 ohm resistor only, because in always remember, as I told you in video lectures also, that when the parallel combination is there, your resistor will always decrease, the equivalent resistance will always decrease. Suppose you have 1 2 3 4 5 like that random numbers of resistors you have, so whatever the least value of resistor is among them, suppose 1 is the least value, the smallest resistor, so your answer should be less than that. Okay, 3 2 5, so your answer should be less than 3 in the parallel combination. So this is what the strategy I told you all already, so you can recheck your answer as well from this part. Now they are in, now from A to B, RAB equivalent resistance will be R1 plus R equivalent first, which we have calculated, yes, yet, and then R4. You can also write this pattern as RAC plus RCD plus RDB. You can use any of the pattern. AB is equal to 5 plus 5 plus 5. Don't forget to write the unit. This is the equivalent resistance of the circuit. Okay, so we are done with this question. Now let us move to the next question. So the next question of the physics part is define electric power with respect and write its SI unit. As I told you, if you know the formula of heat, you just have to divide that formula from the time, because what is power? Power is nothing but work only with respect to with the rate of time, how much time we consume to do that amount of work. So on a unit time, what amount of work I have done, that is why my potential, but that is my power. Okay, so electric power P is equal to W upon T, work done, or heat. If you talk about that all the work done is in the form of heat, so we have this pattern. So we have V I T upon T, which is equal to V square upon R into T I square R T. What we have to do? We have to simply divide it by T, the heat formula, and what the conclusion we get is power is equal to Vi is equal to V square upon R is equal to I square R. This is what the general formula we have. Okay, so if we talk about the next point is the two bulbs rated 100 and 100 watt and 100 watt and 220 volt, and the another bulb is of 60 watt with 220 volt, are connected in parallel to an electric mains. Suppose we have an electric mains, and this electric mains is of 220 volt. Now this is connected with a bulb of some rating which is given to us. This is the first bulb, and the first bulb is with a rating of 100 watt with a 220 volt. Another bulb is also connected, and this bulb is of 60 watt with a 220 volt. So the potential provided to individual bulb is the same, and they are connected in parallel to the mains. Okay, fine, and their voltage are given different. Okay, find the current drawn by the bulb from the mains. Okay, how much is the current drawn by the bulb of 100 watt? This is I1. How much is the current drawn by this bulb as I2? So if we need it, if we find the value of I1 plus I2, that will be the total current drawn from the bulb, from the mains by the bulb. Okay, so if I talk about I1 part, so first we have to see the formula of power, because power term is given 100 watt. So we are going to use the formula of power only. So P1 is equal to V1 I1. P1 is 100 watt, which is equal to 220 volt of supply into I1. So we will get the value of I1 as 100 upon 220 ampere. The second part, if I talk about I2, I'm directly writing that is P2 upon V2, which will be 60 upon 220 ampere. This is what the value of I2. So total current drawn from the mains is I is equal to I1 plus I2, and that would be, because you can see, find the current drawn by the bulbs. It means it is talking about the total current drawn from the mains by these two bulbs. Okay, so I will be I1 plus I2. So I is actually 160 upon 220 ampere. This is the value. You will sort it out. This will be 8 upon 11 ampere, or you can write it in the decimal as well. Okay, so this is the total current drawn from the mains by the electric bulbs. Okay, now we are going to talk about the Joules law of heating. As I already told you when I was explaining the power formula, so heat is the amount of work done only by the electrical energy, by the charges when they move, when they rushes, when they drift, then they generate in a resistor, then they due to the collision of the charges, due to the opposition which they accept from the, which they resist in a resistor, there is a heat generation, and that too we talk about from the formula VIT, V square upon R into T. Time is also included for how much a time they experience such situations. That is what determines the how much is the energy. Okay, so the next part, if I talk about, so basically they are asking this formula only as per the question. Okay, the Joules law of heating express it mathematically when an appliance of resistance R is connected to a source of voltage V and current I flows through the appliance for a time t. So VIT they basically are asking. Now if we talk about the next point of the question, 5 ohm resistor is connected across a battery of 6 volt. Calculate the energy that dissipates as a heat in 10 seconds. Suppose this is any resistor, either in either nichrome wire or any of the appliance, either bulb, any appliance generating the heat. This is the key connected. This is the battery provided. Now the potential difference of the battery is given to you, that is 6 volt, and this 6 volt will be provided to this resistor which is 5 ohm. Now the question asked is what is, calculate the energy dissipated in the time of 10 seconds. So in 10 seconds, how much is the energy dissipated? If I talk about the formula written, so we have this formula, we can use this. Now we do not need to find out the value of current. We can directly use this second formula because potential difference and resistor is already given. So we will use V square on R into T, the formula. So V square is 6 into 6 divided by 5 into the time is 10 seconds. So what we get the formula 36 into 2, which is equal to 72 joule. So this is the amount of heat energy dissipated in 10 seconds by the resistor of 5 ohm. Okay, now let's move to the next question. The next question is, a student fixes, this is the case study part, the last question of the question paper. A student fixes a sheet of white paper on a drawing board using some adhesive material, and she places a bar magnet in the center of it. Okay, let us draw the situation. So we have a plain sheet of a paper which is fixed on a cardboard, and we have the bar magnet placed at the center. Suppose this is the bar magnet. Suppose this is the bar magnet which is placed at the center. This is south pole, this is north pole. Okay, fine. So, and it sprinkles some iron fillings uniformly around a bar magnet using a salt sprinkler. You are eating the food, you are sprinkling the salt. So from that only the iron fillings are being sprinkled basically homogeneously on the entire paper. The iron filling is being sprinkled. Now what we experience on tapping the board gently. Now when we tap the board means when we basically vibrate the board, so that these particles to vibrate to little come up from the surface of the plane, and as they come up they align themselves. Let us see the question, then I'll tell the answer. She observed that the iron filling has arranged themselves in a particular pattern. So basically what type of pattern it is, it will be asking in the questions. A part asks that draw a diagram to show this pattern of the iron filling. So we very well know the pattern. The pattern will be this way. The lines coming out from the North Pole terminal. Somewhat this is the pattern. I'm just drawing the pattern. This will be the pattern. And we know that from the North Pole and South Pole, the lines are being arranged Always remember that the two lines should not intersect each other, and there should be no edges. It should be flexible curves. Okay, so ultimately we have this shape of the iron filling. This would be the shape as per the traced lines we very well know. So draw the magnetic field line of a bar magnet showing the pole of the bar magnet as well as the direction of the magnetic field line. I already drawn the direction as well. From the north to south, it moves outside from the bar magnet, and from inside it moves from south to north. The field lines I'm talking about. Okay, the directions. Okay, now the C part says, how is the direction of magnetic field line at a point determined using the field lines? Why do two magnetic field line do not cross each other? The first part I already answered. Now if I talk about the second part, why do the two magnetic field line does not cross each other? Suppose this is the magnetic field line and they crosses each other. Now when they cross it, this is the point of intersection. If I zoom this point, this is the point. And if I talk about this point, we would be having this tangent, this tangent, this tangent. We can have many of the tangents. Basically two tangents we are talking about. So we have two tangents, which says that magnetic field line, a single magnetic field line or a magnetic field line. What type of magnetic field line? Uniform magnetic field line can never intersect, because at a point of intersection it has two direction as mentioned by the tangents. When the tangents are drawn, it shows the two directions, which is not possible. So two directions at a single point is not possible. Okay, if I talk about this curve line of the magnetic field, you can see at individual point, if you draw the tangent, you will get a single direction of the magnetic field. Okay, so direction of the magnetic field changes as per the curve lines are there, but at a single point tangent, only single direction should be there. This is actually the law. So it cannot have the two directions at a single tangent. At a single point, it cannot have the two different directions represented by the tangents. So that is why they never intersect. This is one of the reason, and they are maintain themselves apart. They do not intersect. Okay. So this is what the paper done. The paper was quite easy as per the questions we did in the sessions. So thank you and have a nice day.